Good morning, students. I was waiting for more students to join, but I think no one else will join now because this is all revision classes. At least 14 students have joined. I should be happy with that number itself. Okay. Anyway, let us proceed with today's class. We have been discussing the additional exercises that are present in my notes. Now, this is the last exercise that is present in the first module. In the second module, I don't have any additional exercises. That is because it is basically source coding, and we had already performed many exercises in that module. So after the completion of this particular exercise, I'll be directly going to the third module's additional exercises, which I had not discussed during the regular course of teaching learning. So let us proceed with this exercise now. For the state diagram of the Markov source shown, verify G1 greater than G2 greater than H. This expression I had discussed earlier. When the symbols are statistically dependent, when we combine more symbols into a sequence, now naturally the number of bits which we have to send through a sequence will get reduced. That way we save the information rate, or we reduce the information rate. When we reduce the information rate, we can match with the channel capacity. They're all related that way. You already know about channel capacity as well. So we should take care that capital R is less than or equal to capital C. Now if capital R has to be less than or equal to capital C, if R is lesser, naturally G2, G3, G4, that way if we combine more symbols into a sequence, the number of bits that we are going to send is going to be reduced. That is the outcome of this expression now. So G1 should be greater than G2, G2 will be greater than H, that way it goes on, G3, G4, G5. The least is the source entropy H itself. So for the state diagram of the Markov source shown, verify G1 is greater than G2, G2 is greater than H. Now why H itself is the least out of all these? Because in the case of H, it is the source entropy itself considering the symbols themselves, not considering their transmission as such. It is considering the probability of occurrence of the symbol at the source. But when we consider G1, G2, G3, G4 that way as a sequence, we consider the transmission of the symbols in the channel. That is the idea here. Now this is the state diagram where we have two states, state 1 and 2. In the first state, the probability of A being transmitted is 2 by 3. And naturally the probability of C being transmitted is 1 by 3. And in state 2, the probability of B being transmitted is 3 by 4. And the probability of C being transmitted is 1 by 4. That way we have three symbols A, B, C here, but actually the state 1 is going to emit only A and C, and the state 2 is going to emit only B and C. Now, as the state probabilities are not given here, in general case we assume it to be 50% of half and half. If it is 3 states, we consider it as 1 by 3, 1 by 3, 1 by 3. But it is always a good idea to calculate the probability of the state using the state equations. So let us write the state equations here now. P1 is equal to 2 by 3, 1 plus 1 by 4 into P2. How? This is written based on the symbols being received at the state, right? So 2 by 3, A is received at state 1. And C is received at state 1, and C is obtained from state 2. So it is 2 by 3 P1 plus 1 by 4 P2. Similarly, P2 is 1 by 3 P1 plus 3 by 4 P2. State 2 is receiving C, and the probability is 1 by 3, and it receiving B is 3 by 4. So that way 1 by 3 P1 plus 3 by 4 P2. Now we have two unknowns and two equations. Solving them, we can solve this way. By solving them, we get P2 equals 4 by 7 and P1 equals 3 by 7. As I have been telling you always, it is better that you also work out all these exercises on your own to become familiar with these procedures. We have the value of P1 and P2. Now the entropy of each state is H1 is 2 by 3 Lg of 3 by 2. That is summation of capital Pi into Hi, right? So that is 2 by 3 Lg of 3 by 2 plus 1 by 3 Lg of 3 by 1. So that is 0.9184. In the case of H2, it is 3 by 4 Lg of 4 by 3 plus 1 by 4 Lg of 4 by 1. That is 0.8113. Depending upon these A and C symbols only. So H is P1 H1 plus P2 H2. This is the entropy of each state, H1 and H2. Now, total entropy of the source is H equals summation of Pi into Hi, that is P1 H1 plus P2 H2. We get the value 0.8572 bits per symbol. Now, this is the entropy of the source. Now, we have to find out, we have to prove that G1 is greater than G2 greater than H. That means we have to write the tree diagram corresponding to G1 and G2. We already have the value of H now. So the tree diagram let us write, because we want to have G1 also, G2 also, we will have to consider two symbol emissions now. So the tree diagram for the given state diagram is written. Let me zoom in. You can see both the diagrams now. You can see now also. So from state 1, the probability of the state is 3 by 7. It is emitting A and it is emitting C. Then again, when it is emitting A, it is coming to state 1. From state 1, again it is emitting A, it is emitting C. That way we have the sequence AA, AC. This is corresponding to G2. And this middle one is corresponding to G1. Now again from state 1 to state 2, when it is emitting C, from state 2, again it is emitting C and it is emitting B. That way it is CC and CB. Then it is coming back to state 1 and state 2 respectively. Now from state 2, with the probability 4 by 7, it is emitting C, it is emitting B. And after emitting C, it is emitting, after emitting C, it is coming to state 1. And then it is emitting A or it is emitting C. That way we have CA and CC. Now, when it has emitted B, again from B, it is emitting C or it is emitting B. Based on that, we have BC and BB. Now we have G1 and we have G2. In G2, we have these many sequences: AA, AC, CC, CB, CA, CC, BC, BB. Now you can see there are common sequences. CC is common here and here. Only CC is common. No other sequence is common. AA is not commonly occurring anywhere. So when we calculate G2 for CC, we can simply add these two. 2 by 3, 1 by 3, 1 by 4, 1 by 3 in our calculations. Otherwise all others are individually occurring sequences that way. Only CC is occurring twice. Other sequences are occurring only once. That is corresponding to G2. Now this way when we proceed, let us proceed now for the calculations. P of A with reference to the state diagram now. P of A is 3 by 7 into 2 by 3, 2 by 7. P of B is 4 by 7 into 3 by 4, 3 by 7. P of C is 3 by 7 into 1 by 3. But C is occurring here twice. You can see here from state 2, it is emitting C. So this is 1. Let me change the color. From state, wait a minute. From state 1, it is emitting C, that is here. It is emitting C. And from state 2, it is emitting C, that is here. So you can see emission of symbol C is happening twice here. Whereas from state 1 it is emitting A, that is here, and from state 2 it is emitting B, that one is here. So that is how for C we have two occurrences. That is how we calculate P of C now. P of A is straightforward, P of B is straightforward. State probability into the symbol probability. Whereas P of C is having state probability into symbol probability plus another occurrence. We get 2 by 7. Now G1 is what? G1 is 1 by n into summation of all those sequences or symbols. In this case it is symbols, it is not sequences. So that way 1 by 1 into summation of all these, you get 1.557 bits per symbol. Now proceeding with G2. P of AA is found out accordingly. P of AA, P of AC, P of CC, CC is occurring twice as we have seen earlier. And then P of CB, state probability into the transition probability is here, right? It is a state to state transition where the symbol has a probability there. That is now called as transition probability in terms of Markov sources. So you can see that we have computed all the probabilities of the sequences taking two symbols in a sequence. Using this, now we will calculate G2. That G2 is now 1 by n. N is 2 here. 1 by n into summation of all those probabilities correspond to their entropy. So we get the value 1.3085 bits per symbol. G2 is 1.3085. G1 is 1.57 and H is 0.8572. You can see here H is 0.8572, G1 is 1.5567, G2 is 1.3085. This way you can see G1 is greater than G2, it is greater than H. Still, if we want to conserve the data rate at the source, we can go for G3, we can go for G4, we can go for G5 that way. By combining more and more symbols into a sequence, we can save the data rate at the receiver. If R is lesser, then automatically R can match with C, the channel capacity. And if R matches with the C, always we can detect the error and correct the error at the receiver based on the channel coding theorem's statement. Now I hope you can recall all these fundamentals also along with the bigger picture. Now when I was discussing the first module at that time, you might wonder why all these complicated diagrams and why all these repetitive computations or calculations. But they had a purpose that way. As we have completed all the 5 modules, now you can relate each one with the other concept and you can understand the importance of these things. Now this is the end of the first module. The other summary I have already discussed earlier. In the second module, I don't have any additional exercises. Let me directly go to the third module. This was the Muruga's method, after which I have additional exercises in the third module now. Now this is the third module with the channel capacity. So there are not many additional exercises. I think there is only one here now. That is only a derivation which I did not want to discuss in our main process because it is again a repetitive task there. Now anyhow, we have the goal of going through everything that is there in our notes. That is why let us proceed this way. Additional exercises. Exercise 14 in the third module. Prove that the mutual information of a channel is symmetric. Mutual information of a channel is symmetric. That means I of A semicolon B is equivalent to I of B semicolon A. Now if you visualize that diagram with the two circles, at the left side you will have H of A slash B, at the right side you will have H of B slash A, and at the middle you will have I of A semicolon B. That is the mutual information. Wherever there is an overlap of two circles. Now, otherwise also it is mutual. Even in the common sense also, if you think I of A semicolon B is I of B semicolon A only, that way. But as such, human beings want proof for anything and everything which can be proved. That is how science and engineering and technology are coming into picture. We cannot prove something even by our own common sense also in the case of technology, science and engineering. Of course, we can prove only in philosophy that way when we have personal experiences. We need not prove that chili is always hot. We need not have a mathematical proof. Chili remains hot. And if somebody asks the proof for chili being hot, we have to ask him to put one chili into his own mouth and he has to chew on it. Then he will understand that chili is hot. For such things, there is no need of any proof because it is a personal experience. But here in technology and in engineering and in science, it is not a personal experience as such. It's a personal learning as such, right? Of course, many times experience leads to learning. But in the case of technology, these things cannot be experienced. They have to be learned in this way only. That is where we have proof. That's all. Let me stop my blabbering now. Let me come to the topic now. Prove that the mutual information of a channel is symmetric. The answer is, we know that I of A semicolon B equals summation of I equals 1 to M and summation of J equals 1 to M, P of AI comma Bj, this is a joint probability, into Lg of P of AI slash Bj divided by P of AI. This is by definition itself, right? This is how we have mathematically defined the mutual information. With respect to our discussion of conditional probability and joint probability. This is the conditional probability, this is the joint probability. Using them, we had defined mutual information mathematically. Now from Bayes theorem, we know that P of AI comma Bj is equal to P of Bj comma AI. Please recall Bayes theorem, where if you have a numerator and denominator at the left side, numerator, denominator at the right side, if you arrange the Bayes theorem that way, you will get it as P of AI comma Bj is equal to P of Bj comma AI. Joint probability is mutual there. Now, P of AI slash Bj divided by P of AI is equal to P of Bj slash AI divided by P of Bj. This is again from Bayes theorem only, right? Now, P of AI slash Bj into P of Bj is equal to P of Bj slash AI into P of AI. That way the joint probability is symmetric. And this ratio is also symmetric now, again from the Bayes theorem only. P of AI slash Bj divided by P of AI is equal to P of Bj slash AI divided by P of Bj. We can use this terminology here also. Wherever we have this Lg of P of AI slash Bj divided by P of AI, we can replace it in this way also, that P of Bj slash AI divided by P of Bj. And this P of AI comma Bj, we can replace it as P of Bj comma AI also, because they are symmetric. Now, when this is symmetric and this is symmetric, naturally mutual information is going to be symmetric. Again from the Bayes theorem only, right? So that way, when this ratio is symmetric, log has nothing to do with the symmetric nature, right? Log has only a functionality. Logarithm is a function for a given value. So log has nothing called symmetric and asymmetric nature. And the joint probability itself is also symmetric. So ultimately, mutual information is symmetric. We will see that now. So we can write it as I of A semicolon B equals summation of I equals 1 to M and summation of J equals 1 to M, P of Bj comma AI into Lg of P of Bj slash A divided by P of Bj. We are replacing those terms with these terms now. This is nothing but I of B semicolon A, which simply means the mutual information is symmetric. I of A semicolon B is equal to I of B semicolon A. Mutual information is symmetric. This we have mathematically proven. As I told you earlier, some things which cannot be learned by experience have to be learned by mathematics. That way, mathematics is a great tool for using logic with the concept. Without the mathematics, there is no engineering possible at all. There is no technology possible at all. To some extent, science may be possible. Why? Science is also physics, also chemistry, also biology, also maths, right? Science is basically physics, chemistry, maths, biology together. So to some extent, in chemistry, mathematics will not work. In biology, mathematics may not work. In physics, it is mathematics which is already working. All the physical quantities are mathematically expressed. But the chemical equations are not always following the mathematical theory. To some extent, there is mathematics in chemistry. But otherwise, the properties of each element is not guided by mathematics as such. Or the combination of two chemical compounds to form some other compound is not actually mathematically guided. They are their inner nature. That is where comes biology also. Biology is a mysterious science that way. Life comes out of a cell. Inside cell, we know what all is present there. And the mystery of the cell itself is there is a diffusion occurring through the cell wall, where whatever is required from the outer medium is getting into the inside of the cell. And inside there are multiple parts which are going to use the diffused material which is coming inside the cell in many different ways. We cannot apply mathematics there inside at all. How a mitochondria works, how platelets work, how those ribosomes, lysosomes are going to work, how nucleus itself is going to work, how Golgi apparatus is going to work. We have to find out by means of the mysteries of nature. There maths is not applicable. But in engineering and technology, without maths, nothing else is possible. Engineering is basically applications of physics only, right? Mostly it is physics, to some extent chemistry. And utilization is for biology or for life. That way mathematics is a great tool. Let me stop my blabbering once again. Anyhow, it is a revision class, so I am blabbering more with some other thing. Of course, everything what we discuss or we think will be useful to our life in one way or the other, because every day is learning only for us. Let us see the next exercise now. Exercise 15. Show that h of a comma b is equal to h of a slash b plus h of b. Diagrammatically, you remember the joint entropy of the sources is equal to equivocation plus entropy of the destination. It can be written the other way also, h of b slash a plus h of a. That way also it can be written. We have seen that. Now let us try to mathematically prove this by using the basic definitions. We know that h of a slash b, let us write the expression for equivocation. It is the summation of I equals 1 to m, summation of j equals 1 to m, p of ai comma bj, lg of 1 over p of ai slash bj. Now h of a comma b, the joint entropy is summation of I equals 1 to m, summation of j equals 1 to m, p of ai comma bj, lg of 1 over p of ai comma bj. Because this is a joint entropy now, where we had only a conditional probability. To the conditional probability, we have to add the symbol probability. So we get this p of ai comma bj, which is the joint probability. Now h of a comma b is by definition this way. Let us split it now. Summation of I equals 1 to m into summation of j equals 1 to m, p of a comma bj into lg of 1 over p of a slash bj into p of bj. That is the expression for the joint probability. Now let us split further. Summation of I equals 1 to m into summation of j equals 1 to m p of a comma bj into lg of 1 over p of a slash bj plus summation of I equals 1 to m into summation of j equals 1 to m p of ai comma bj into lg of 1 over p of bj. Why? We purposefully multiplied by this term lg of 1 over p of a slash bj. Okay. Now we multiplied it to this term and we split it further. Because the summation is applicable to the complete things, we are splitting this right hand side term in this manner. P of a comma bj lg of 1 over p of bj. Okay. So this is split, this is split, that's all. When that is split, you can see that term here also. That is where we have this plus term here. Now let me stop this annotation and let me start annotation again. What is this term now? When we took this term, and this term separately, we put the plus term here. What is this term now? This term is h of a slash b. This is nothing but the equivocation, right? And below we have summation of I equals 1 to m, summation of j equals 1 to m, p of a comma bj lg of 1 over p of bj. Now this is h of a slash b, and what is this term totally? This is nothing but h of b. Now this summation of I equals 1 to m, that joint probability can be completely taken out. This summation term from the joint probability can be taken out, and we can simply write summation of j equals 1 to m of p of bj lg of 1 over p of bj, considering the expression for the joint probability. Now this is nothing but h of b. Why? Consider the joint probability, that summation of I equals 1 to m of p of ai, that is going to become 1 there, right? It is unity there. That unity into this whole term, that is going to be h of b. This way h of a comma b is equal to h of a slash b plus h of b. Now similarly it can be shown that h of a comma b is equal to h of b slash a plus h of a, just by rearranging the same terms in the same manner. Instead of writing in terms of bj, we can write in terms of ai itself here and in terms of bj slash ai here. That way we can prove that h of a comma b is equal to h of b slash a plus h of a. Now coming to the next exercise. Show that h of x slash y is equal to 0 when x is equal to y. Equivocation is going to be 0 when the two circles map with each other. Two circles merge with each other. You can visualize those two circles. When those two circles merge with each other, that is 100% transmission of the information at the receiver. No noise at all. Naturally, equivocation is going to be 0. Mutual information itself is going to be the information of the source itself. Now we have to mathematically show that. Let us see. Using the same fundamental definitions of these terminologies, we can prove that. We know that h of x slash y is equal to summation of I equals 1 to m into summation of j equals 1 to m into p of xi comma yj lg of 1 over p of xi slash yj. Now, what is p of xi comma yj? It is p of xi slash yj into p of yj by the definition of the joint probability. So we are substituting this here. Instead of this, let us substitute this. Okay. Now, summation of j equals 1 to m of p of yj into summation of I equals 1 to m of p of xi slash yj into lg of 1 over p of xi slash yj. this summation, let us bring it here. Summation of I equals 1 to m, that we can bring it here. Can we bring it that way? We can bring it because it is with respect to conditional probability. And this p of yj along with that p of j equals 1 to m, that we can bring it this side. Because this is with respect to the receiver itself. That way we can move the summation to the right side by putting p of yj into that summation function. Now using this, when x equals y, it is a lossless channel, right? When x equals y, it is a lossless channel. Means p of xi slash yj is equal to 1 for I equals j. And for p of xi slash yj is equal to 0 when I is not equal to j. You will have to remember that matrix where we have identity elements from left to right in the diagonal. And for all other elements, we will have 0. Because when the source is sending that symbol, receiver is receiving that symbol. That way when x is equal to y, the conditional probability is equal to 1 when I is equal to j, and it is 0 when I is not equal to j. So now, when the conditional probability xi slash yj itself is going to be 0, what is going to happen here now? H of x slash y is equal to summation of j equals 1 to m of p of yj into 0, that is going to be 0. This way, we have mathematically proven that when the transmission is 100% without noise, equivocation is 0. Mathematically, we have proven that. Moving on to the next exercise. This is the last exercise. With this, I am ending. Exercise 17. Show that h of x slash y is equal to h of x when x and y are statistically independent. Equivocation is equal to source entropy itself when x and y are statistically independent. What does it mean? They are statistically independent means the circles are not at all merging. Circles are totally separate. In that case, equivocation is fully there. No transmission at all. It is 0 transmission there. Whatever is received at the destination is purely noise. That is the meaning here. That is the meaning of statistical independency. Otherwise, if destination is dependent on the source 100%, then we should say x equals y. If the destination is not at all dependent on the source, then it is not destination, this is not source actually, because there is no communication there. If x equals y, then the communication is 100% completely noise free. If x is completely not equal to y, then there is no communication at all. Whatever is at y is noise. That is the meaning here. So show that h of x slash y is equal to h of x when x and y are statistically independent. We know that mutual information I of x semicolon y is h of x minus h of x slash y. Right? This we had proved also mathematically. Now when x and y are statistically independent, mutual information itself is 0. When mutual information is 0, h of x minus h of x slash y is equal to 0, or h of x slash y is equal to h of x. On the other hand, we can also write h of y slash x is equal to h of y also. We can write it that way also, considering the destination. H of y slash x is equal to h of y also. Because whatever is the receiver receiving, that is the equivocation with respect to the source. But as there is no communication, there is only noise. That means the source symbol did not reach the destination. None of the symbols reach the destination. It is completely noise. In such a case, we can prove the same thing by taking the other definition of I of x comma x semicolon y with respect to the receiver. We can prove the same thing as h of y slash x is equal to h of y by writing here as h of y minus h of y slash x. It is obvious now. If you write I of x semicolon y as h of y minus h of y slash x with respect to the destination. Now h of y slash x is equal to h of y. So with this, I am coming to the end of this additional exercises of the third module. I will be ending the class now. In the next class, we will see if there are additional exercises in the fourth and fifth modules, and we will cover them up. See you in the next class. Until then, take care and goodbye.